Okay, so let's look at permutations now in greater detail. You've seen the word pop up a few times in previous videos, and that's because permutations are really just the fundamental counting principle, which I will say is the FCP. So when you're working with the fundamental counting principle, you're pretty close to working with the permutation. And what I mean by pretty close is that there's actually two things you got to keep in mind for permutation. First, with fundamental counting principle or permutation, order matters. So when we're making our spaces and multiplying stuff together, it might not have been really obvious to you, but if you look back at those earlier examples, order matters, and we were counting order. And the best way to think of that is AB and BA were both counted as different items. Okay, and the other thing that you have to keep in mind, it wouldn't have been obvious with the fundamental counting principle until you establish some guidelines, is no repetition. Can't repeat items. So we'll say no repetition. So when you see the word permutation, what I want you to say to yourself is, okay, I'm going to use the fundamental counting principle, which is including order. And most importantly, when I do set up my fundamental counting principle, I'm not allowed to use repetition. And that's basically the definition of the word permutation. And we've been using, I guess, up to this point, notice I was trying to choose my words carefully. I was referring to these, the stuff we were counting as arrangements, and possibly words sometimes if letters were involved. And the word arrangement is actually just a more general word, which includes everything we've been counting up until this point. So a permutation is a specific kind of an arrangement where order matters and repetition is not allowed. So let's look at an example. We'll go back to some letters, of course. We'll take the letters. How about we take A to Z? Take the letters A to Z in the English alphabet. And now I'm going to say how many. How many ways can we arrange these letters? Which was old wording. How many ways can we arrange all 26 letters? Now, of course, that wording is not really clear. Can we repeat? Does order matter? Well, of course, we're going to use all of them, so we can't repeat anything. But I'm just going to update our wording a little bit. I'm going to refer to these things now as 26 letter permutations. And then I think it should be clear what we have to count. And of course, that's the intent, is to know what a permutation is, but of course to be more clear. So if I say arrange all these letters are 26 letter permutations, you say, okay, order matters. So I'm just going to set up my fundamental counting principle, and I'm not allowed to repeat. So of course we'd start off with 26 letters. We'd go to 25 letters since we're not allowed to repeat. And I don't think we have to go all the way down to 1. Once we establish that we are going all the way down to 1, you realize the fastest way to get this on your calculator, of course, is to type in 26 factorial. And believe it or not, that's actually something called a permutation. So we're going to check that on our calc, and of course probably going to get scientific notation here, but you can round that to however you wish. Let's get used to this notion as well, that we are actually dealing with a permutation. Since we have 26 letters that we're choosing from, we use a capital P to say from those 26 letters, I'm going to take a subgroup of 26 letters, of course, where I can't be repeating, and order matters, and that is actually the same as 26 factorial. And you've probably have seen that P on your calculator as you were looking for the factorial button previously. So let's check both of those numbers on our calculator to make sure, of course, that they're both the same. Okay, so we'll go 26 factorial. And remember, that's could be in a variety of locations on your calculator, but in Texas Instruments, it's in a probability menu. And there it is, factorial. So if I go 26 factorial, yeah, no surprise, this is 4.0, we'll say 0.3 times 10 to the power of 26. It's a ridiculously big number. So if I want to use that P button, which represents permutation, you can see it there, number 2 in my submenu. Notice I had to type in the 26 first. So if I wanted to use all 26 letters and create a 26 letter permutation, Remember, order matters and repetition's not allowed. We get exactly the same answer. So let's maybe close that down. Let's take another example where maybe I'll just call that, I'll just put a B here. We'll call that first one letter A. Of course was 26 letter permutations. So this one will be, why don't we say 5 letter permutations? So we're going to try to count 5 letter permutations using, of course, the letters A to Z. And maybe we should scroll this up a little bit. There. If I can get rid of that. There we go. So how many 5-letter permutations are there? Then, of course, you have to keep in mind if it's permutations, we can't repeat. So we got to start counting down. 26, 5, 24. And why don't we just get our spaces set up first, which might be the safest way. 26, 25, 24, 23, and 22. Now, of course, we can't just stick a factorial because this thing has to shut down right at the number 22. So between 26 and 22, even though if you subtract those, we kind of trick ourselves into thinking there's 4 numbers. It's actually 4 spaces or jumps between those numbers, but there's 5 letters involved. And this is getting a little bit annoying to type into our calculator. And here's where maybe this notation be a little bit of a time saver. So if I want to do a permutation of size 5 taken from that larger group of 26 things, this will give me the same answer, which we will, yes, check on our calculator right now as well. Okay, so let's go, I guess, the slow way here first. 26 times 25. On these virtual calculators, this is really time consuming, but of course it's not really a big deal if you're punching in with a couple of thumbs. 26, 5, 4, 3, and 2. And at least we're at a scientific notation here, but of course we still have a big number. What is that? 7.8 million approximately, or 7.9 million approximately. And let's verify that if we use, let's slide this over. If I use that 26p5 notation, and notice I forgot to put in my 26 first. Make sure I do that. I forget that probably at least half the time. Number 2 is the permutation button, and if I take 5-letter permutations, we get, of course, the same answer, which we'll scribble down here in yellow, and I lost my calculator. There, brought it back because I don't trust my memory. That's 7 million. Okay, I'm going to have to trust my memory here. What is it? 7,893,600. 7,893,600. And of course, a little bit more convenient going 26p5. Okay, how about one more permutation, and then we'll look at a generalized formula for permutations, which isn't super useful, honestly, until we get into the next topic in this chapter, but I think we'll introduce it now. This time now is as good as any time. So let's take 3-letter permutations. Of course, all this is doing is affecting that second number in that P notation. Permutations. Or they're using A to Z in the English alphabet, of course. And maybe I'll try to scroll this up a little bit. If the wheels don't come off me here technologically again. Here we go. So 3 spaces, 26, 25, and 24. And of course, probably just easy enough to type that in, but I want to convince you that this notation also works, whether it's more convenient or not. It's probably not the case here. But 26 P3 is taking a permutation of size 3 from 26 distinct items, and please keep in mind that those items have to be distinct because no repetition is allowed here in this context as well. So let's check this on our calc. Okay, so 26, 5 times 24. That's pretty straightforward to type in. 15,600, and while we're here, of course, we'll double check our permutation button on our calculator, which is actually using a formula. Remember, that was size 3. We still get the same answer, which is much easier for me to memorize. 15,600. No technical glitches that time. Okay, wrong color, but hey, who's keeping close score and all that stuff. Okay, so let's see if we can formulate a formula for this, which you just have to be aware that it exists. And again, I should feel that it's not super useful right now, but it will be, like I say, in the next topic that we'll look at. So if you were to look in your textbook, maybe we'll do this in red, that you'll see a permutation formula generalized that if you're selecting from n things, and remember this is our 26 letters in the series of examples that we did here, and you're choosing permutations of size r, that actually is set up as a pair of factorials. It's going to be n factorial on the top, all the way down in the bottom. We have to put an n minus r factorial. So believe it or not, this is a formula that just summarizes what we've been doing throughout these last couple of examples. Okay, so let's actually use it with 26 P3. So we put 26 factorial on the top. Right, that's the n. And maybe we'll label that. That might be helpful. We'll say n is 26, and this is our r is 3 in our formula. And on the bottom, the weird part of this formula is why are we putting this difference on the bottom? If I can get rid of this thing. Is it going to go away? There it is. 26 minus 3, of course, is 23 factorial. Now, it might not be really obvious why that subtraction's here until we pull that apart. Now, notice 26 factorial, that does go down to 1. But, of course, we don't want to go down to 1. Remember, we want to stop at 24, which means I want everything after 24 to go away. And what happens after 24? Yep, that is 23 factorial. So that is just kind of a slick way of predicting what number you're going to have to stop at with the factorial still attached. And if you divide by that, guess what? It disappears. So we can cross that off and cross that off, because that 23 factorial will divide and cancel that 23 factorial on the top. And if you look through that and ponder that for a few moments, you'll realize that that is just basically reproducing the fundamental counting principle for you. Okay, so there is your permutation formula. I'm not sure it should feel super helpful right now, but know that it exists, and remember it's basically a special case of the fundamental counting principle when you're working with permutations and using this formula, which is built into your calculators. And those two conditions, of course, are no repetition and order matters.